Hello, for this problem we've got a surface force that's acting over both the x and the y directions. So the magnitude of the force is 30 minus 5 times the x value plus 10 times the y value. And units of this are going to be pounds per foot squared. So with this we've got two dimensions to worry about. And we're asked to determine the magnitude and point of application for the equivalent point load of the distributed force shown below. The original problem scenario online has an explanation of this as sand piled up into a corner like this. So we've got, this is our function, and we need to determine the force function that's kind of given to us, but also the bounds of this. So since we've got x and y, we're going to need to evaluate with respect to, or integrate with respect to x and integrate with respect to y. So our force, our FEQ, is going to be equal to the integral from y min to y max. So the integral from y min to y max of the integral from x min to x max of our force function. So 30, let's just do f of x comma y for now. So we integrate with respect to x first, and then once we find that integral, we integrate with respect to y. Alright, so we also need to find these bounds, so y min, y max, x min, and x max. We've already got the force function taken care of. So let's look at this over here. So this right here is a top view of our problem right here. So if I look straight down, I'm going to look at x min and x max, and I can quickly figure out, based on this, where they would intersect 0. So if I ignore the x, I'm just looking at the y. So 30 minus 10 times what value of y will give me a value of 0. The answer to that is it's going to be 3 feet out this way. And similarly, we can do that with x, and we find it's going to be 6 feet out this way. But what we actually need is something different for the x max. So for y min and y max, that's going to be simple. We are going from 0 feet in the y direction out to 3 feet. For x min and x max, what we're actually looking for is since we're integrating over the length of y, it needs to be for any value of y. And so x min is over here. That's always going to be 0. But x max is this line out here. So it's 6. Right here, but if I look at a different value of y, it only goes out part of the way. So x max is actually going to be an equation. And the equation of this, so for any value of y, x max is going to be equal to 6 minus 2 times y. So that's the value we're going to end up plugging in for our x max. And again, x min, that's always just going to be, x min is on this side over here, that's always going to be 0. So there are our bounds for the whole problem. So let's go a little bit further at this point. So FEQ is going to be equal to the integral from 0 to 3 of the integral from 0 to 6 minus 2y, or 6 minus 2y. F of x again was 30 minus 5x minus 10y. And so we're taking integral with respect to x first. After we take that integral and evaluate it, we're going to take the integral with respect to y. All right, so if I take this integral, this inside integral, I get evaluated from 0 to 6 minus 2y of, well, 30 is just going to be give me 30x, so minus 5 times, so it's going to be 5 halves x squared minus 10y. Since we're evaluating with, or we're integrating with respect to x, we just treat y like a constant here. So it's going to be minus 10yx. And so that whole thing now, we're going to integrate from 0 to 3. But the first thing we need to do is take this, evaluate from 0 to 6 minus 2y. So we've got the, everywhere we've got a value of x, we're going to plug in 6 minus 2y, and we subtract off the minimum value, so since there's an x and everything, minimum value is just going to be 0. So if we evaluate this, it's going to be 30, the integral from 0 to 3 of 30 times 6 minus 2y minus 5 halves times 6 minus 2y squared minus 10 times 10y times 6 minus 2y there. Alright, so we do a little bit of algebra here. Honestly, you can use MATLAB to make this, simplify this function a lot easier. And we can find a value for this algebraic function simplified to the integral from 0 to 3 of 10y squared minus 60y plus 90. So we're taking the integral, and all this, we're integrating with respect to y. Integral of this with respect to y, going from 0 to 3, we're going to get 10/3 y cubed minus 30 y squared plus 90y. And so this is, draw FEQ. And if we evaluate this from 0 to 3, I'm not going to go through the algebra again, but we should end up with a value of FEQ equals 90 pounds at this point. Alright, so we've got a value for FEQ of 90 pounds. So let's go through and we're going to find XEQ. And so let's move this out of the way. And XEQ is going to be equal to the integral from 0 to 3, so this is integrating with respect to y, of the integral from 0 to 6 minus 2y times the force of the force function, so 30 minus 5x minus 10y, all of that times x. And then, so that's the inner integral, the outer integral. So inner integrals with respect to x, outer integral is with respect to y. And this whole thing is going to be divided by FEQ, or that 90 pounds that we just found over here. It's the magnitude of our equivalent point load. All right, so if we do a little bit of work with this top integral, we can find that 0 minus 2y, the integral of all of this times x is going to end up being 15 times x squared minus 5 thirds times x cubed minus 5 times y times x squared. So that's the inner integral here. This 30 minus 5x minus 10y times x, so the integral from 0 to 6 minus 2y. So for this, we need to plug in everywhere there's x, we plug in 6 minus 2y. So this is going to be a bit of a mess. It's going to be 15 times 6 minus 2y squared minus 5/3 times 6 minus 2y cubed minus 5y times 6 minus 2y squared. And so with a lot of algebra actually, or using a program like MATLAB to simplify, we can simplify this whole expression down to negative 20/3 y cubed plus 60y squared minus 180y plus 180. And so that is the integral there. And so we still need to integrate this with respect to y from 0 to 3. And so if we do this integral, we're going to end up with going from 0 to 3. The integral is going to be negative 5/3 times y to the 4th plus 20 y cubed minus 90 y squared plus 180 y. And so if we take that, evaluate that from 0 to 3, evaluate this function from 0 to 3, we divide by FEQ, which is going to be 90. That's going to give us the value for XEQ. And so XEQ ends up, if we do all this math, we end up with an XEQ value of 1.5. And the units, since our original units were all feet here, so feet squared and feet for the dimensions, our units here are going to be in feet. Alright, so that is the XEQ. We can do something similar for YEQ. So Y EQ is going to be equal to the integral from 0 to 3 of the integral from 0 to 6 minus 2y of the force function, so 30 minus 5x minus 10y. And this time, rather than multiplying by x, for the YEQ we need to multiply by y. So times y. And so the inner integral we're integrating with respect to x. Outer integral is 0 to 3. We're integrating with respect to y. And all of this, again, is divided by FEQ, or the magnitude of our equivalent point load. All right? So, if we take this inner integral, it's going to be 30 times 30 minus 5x minus 10y times y. We get a y in all those. The integral ends up being equal to thirty yx minus 5 halves yx squared minus 10y squared. And so we still need to evaluate this whole thing. So we're evaluating from 0 to 6 minus 2y. So we plug in, everywhere we've got an x, we plug in 6 minus 2y instead. So it's going to be 30 times y times 6 minus 2y minus 5 halves times y times 6 minus 2y squared minus 10 y squared. All right, so this is evaluated, and then we would, this is evaluated at 6 minus 2y. We would subtract off the minimum value, which is just 0 in that case. So we're still taking the integral of this whole thing, and if we simplify this out, so you can either do this by hand, or I highly suggest MATLAB again. We evaluate this out, it ends up being equal to 10 times y cubed minus 60 times y squared plus 90 times y. We're taking the integral of that from 0 to 3 with respect to y. So if we take that integral, we end up with the integral being, so from 0 to 3, this is going to give us 5 halves y to the 4th minus 20y cubed plus 45 y squared. And so we're evaluating this from 0 to 3. This is going to be y eq. And we need to divide by our FEQ value, which is, again, the magnitude of the equivalent point load, so 90. And in the end, if we evaluate this from 0 to 3, so we're plugging in 3 every time we get a y, subtracting off 0 at the end for the minimum value, divide by 90, we should end up with a y EQ of 0.75 feet. All right. So we've got XEQ, YEQ, that is the x and y position of our equivalent point load. We've got the magnitude of the equivalent point load. FEQ is 90 pounds. Now we can go back and kind of draw this in. So what would all of this look like? Well, if I copy down my original axes, kind of build a replica of that. I have x, I have y, I've got z. My force is going to be, remember, XEQ was equal to 1.5 feet. So if I go out 1.5 feet this way and go out along the x-axis, or along the y-axis, 0.75 feet. So this is 1.5. This one over here is 0.75. And the magnitude of the force is 90 pounds. This single point load right here is going to be statically equivalent to the distributed load that I started with. So with that, I've solved for my equivalent point load, both magnitude and point of application. We've gotten what we want. So thank you for watching, and I hope to see you again.